All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 2, Section 5. Section 5 begins on page 71, and it's called Special Functions, and the first part of it is Rational Inequalities. It says to solve polynomial and rational inequalities, we use both mathematical and real-world problems and write our solutions using interval notation. So what is interval notation? Well, it says to solve a polynomial inequality, it's helpful to follow these steps. Use mathematical operations to move all the terms to the left side of the inequality sign, so the right side of the inequality is equal to 0. We are going to follow this example as I read, okay? Although it goes on to the next page, so we can only do so much following, but that's our goal here. So it says, express the solution of x to the third plus 4x squared is less than x plus 4 using interval notation. So first we move everything to the left side of the inequality sign, all right, which they've done here. Then you change the inequality symbol to an equal sign and solve. Those solutions are called critical numbers. So change it to an equal sign, solve, okay, they've factored, and they get that x equals plus or minus 1 or x equals a negative 4, okay? Place the critical numbers on a number line with the proper notation. So here's their number line, here's their critical numbers. Parentheses represent less than or greater than, and brackets represent less than or equal to or greater than or equal to. Since our original problem was less than, we're going to be using all brackets. But as you can see, the brackets actually face away from the critical numbers because the critical numbers are not included. All right? Then, which goes on to the next page, so I'm going to read the last two. Test the value of x in each region of the line to determine whether the original inequality is true in that region. So what they mean is you're going to test a value that is less than negative 4. You're going to test a value that is between negative 1 and negative 4. You're going to test a value between negative 1 and 1. And you're going to test a value that is greater than 1. And then see which of these regions is actually true for this inequality. So you're going to test it. I would go back to here. You're going to test each of those chosen values in this equation and see, is it actually less than 0? And then it says, express your final answer in interval notation. So let's turn the page and look at what interval notation actually is. So here we are on the top of page 72. They chose the numbers negative 5, negative 3, 0, and 2, and they've tested them. Negative 5 was true, so that section of the region is correct, right? But the negative 3 was false. The 0 was true, so that center region fits the inequality. And then 2 was false, so that doesn't. So they had two sections of the 4 that they tested that actually fit the inequality. So to express their answer in interval notation, and this, I believe, or I'm pretty sure, where's my pen? This should be negative infinity. So from negative infinity to negative 4, those are good answers. And that is unioned, because we're talking about everything that works, right? With the interval between negative 1 and 1. All right, so even though these look like an ordered pair, that's not what they're doing here. These are intervals. And they use parentheses, again, because the 4 is not included. The negative 1 and the 1, they are not included. The infinity is not included in the answer, but you can go in between those places, okay? Let's look at another example. A ball is thrown straight up from the top of a building that is 128 feet high with an initial velocity of 32 feet per second. The height of the object can be modeled with the equation negative 16t squared plus 32t plus 28. Now, express the times the ball is higher than the building in interval notation is what they're asking. So we need to know when is its height, okay, which is what S of t equals. When is it greater than 128 feet, which is the initial height of the building? So that's how they've set it up. Negative 16t squared plus 32t plus 128 is greater than 128. When they subtract this 128 from both sides, it actually cancels out the constant altogether. So we're left with negative 16t squared plus 32t greater than 0. Okay, moving up to the top of the column, column 2 here. Now they're changing it to an equal sign and they're solving, right? Both of those terms have a negative 16t in common, so they factored that out. So t has to be equal to 0, or this t is equal to 2, right? So we're going to put them on the number line. And we're going to use our brackets because remember, the original equation was greater than 128. Then they're testing numbers, right? We need a number less than 0. We need a number between 0 and 2, and we need a number greater than 2. They chose negative 1, 1, 3. Negative 1 was false. The positive 1 was true. And the 3 was false, which tells me that this region only, okay, between 0 and 2 seconds, this region only is the answer to this problem. That's between 0 and 2 seconds was when it was greater than, or taller than, higher than the building. So this is how we write the interval notation, parentheses 0, 2. All right? We'll do a couple of these when we get to the problem section of the section, I guess. But for now, we're going to go on to the next part, which is rational inequalities, page 73. The process for solving rational inequalities is very similar to the process you use to solve polynomial inequalities. The difference is that now you need to set both the numerator and the denominator equal to 0 to find your critical numbers. Okay? And then here's some steps again. Use mathematical operations to move all the terms to the left of the inequality so that the right side of the inequality is equal to 0. Split the inequality into two equations, one with the numerator of the fraction equal to 0 and one with the denominator of the fraction equal to 0. If a number is a solution to either of these equations, it is a critical number. So whether it's a solution for the numerator or a solution for the denominator, both of those will make it a critical number. Put the critical numbers on a number line with proper notation. Key point: when a critical number occurs from the denominator of a rational function, it is always placed on the test line with parentheses. Those critical numbers can never be included in the solution because the denominator of the rational function cannot equal 0. So what they're saying is, here's the example. I'm going to slide up here, right? Our example is greater than or equal to, and the page before said if it's greater than or equal to, we use brackets, right? But if we're talking about in the denominator, it's still going to be in parentheses because it can never be a 0. We don't want this to be a 0, okay? Then we test the value and express our answer. So let's look at this example. We have the quantity x squared minus 4x minus 12 over the quantity x squared minus 4 greater than or equal to 0. They want you to express the solution in interval notation. So everything is already on the left side of the equal sign, so they take each part and set them equal to 0. X squared minus 4x minus 12 equals 0, x squared minus 4 equals 0, and then they factor, right? Both of these are factorable, and they get that x equals 6, or x equals negative 2, or x equals 2, or x equals negative 2. Now we have negative 2 twice, right? And that's okay, it says. You only need to worry about one. You're not going to write two negative 2's on a number line, right? That doesn't make sense. So top of the column, the next column is our number line already set up. And we have our negative 2, our 2, and our 6. Now look, because the negative 2 and the 2 were both in the denominator, parentheses. The 6 was in the numerator, it gets the brackets. All right, so that's the difference here. Testing the points, okay, they find that the negative infinity to negative 2 works. And they put that in union with the negative 2 to 2. So there's this part works, right? And then that's in union with the 6 and above. So 6 to infinity. But look here, because the 6 is included, we get a bracket, right? And then this side gets a parenthesis because infinity goes on and on forever, amen. So careful where you're putting your parentheses and your brackets because it makes a difference. All right, let's take a look at another example. The average cost per item of producing X items is found by dividing the cost function C of X by the number of items X. Given the cost function C of X equals 50X plus 200, when is the average cost less than $100? Okay, so they set up their equation. They have their C of X divided by X. Okay, the cost of making the items divided by the number of items. They want that to be less than 100. Now, remember, to solve these, we need to move our 100 over so that we have this less than 0. When we do that, we need to combine it with this fraction, right? So we have to multiply 100 by x over x. And that's what they've done here. So now they can actually subtract it from here. They combine their like terms and end up with negative 50x plus 200 divided by x is less than 0. We set the numerator and the denominator equal to 0. Solve for our critical numbers. Plot them. This one's a less than, so it's all brackets. And then there's 3 regions. We have to choose 1, 2, 3 numbers. In this one, the only region that works is over here. So as long as they are, I forget what the actual question is here. When is the average cost less than $100? Sorry. When they make more than 4 items. So if they are making more than 4 items, the average cost is going to be less than $100. Okay? All right, let's turn the page. All right, taking a look at some of these problems. We're on page 74. Problem number 1 says, which of the following is a correct way to express negative 4 is less than or equal to x, which is less than 5, in interval notation? Okay, so the negative 4 is less than or equal to, so that's a bracket. We just put a comma in between, and then the 5 is a parenthesis because x is less than 5. So this would be our answer, which is letter C. Okay. Express the solution to the inequality x squared plus 6x plus 5 is greater than or equal to 0 in interval notation. All right. So we need what factors of 5 add up to give us a 6. Multiply them to get to 5, add to get to 6 is going to be x plus 5, x plus 1 is greater than or equal to 0, and then we solve, right? So x is going to be equal to negative 5, and x is going to be equal to negative 1. They want us to express the solution to the inequality, so we would have to make our number line. We have negative 5 over here, and we have negative 1, and then here's our 0, let's say. So we have to test each of the sections, okay? Does negative 6 make this less than 0? So I didn't quite give us enough room. Negative 6 squared plus 6 times negative 6 plus 5 is greater than or equal to 0. Well, negative 6 squared is positive 36. 6 times negative 6 is a negative 36. They cancel. Is 5 greater than or equal to 0? Yes. So this is, I don't know, this is a good spot, okay? We'll just mark it with a check mark. Between negative 5 and negative 1, I'm going to choose a negative 2. So negative 2, the quantity squared, plus 6 times negative 2, plus 5. Is that greater than or equal to 0? Well, this is a positive 4, but this is a negative 12. So it would be 4 minus 12, which is a negative 8, plus 5, which is still a negative 3. So this is no, it does not work there. I'm going to borrow some of the space from this problem here. And we're going to test 0.5, I guess. Yuck. All right, so we have negative 1/2 squared plus 6 times negative 1/2 plus 5 greater than or equal to 0. So this becomes a positive 1/4. This becomes a negative 3. Still, 5 minus 3 is 2. And so we're still in the positive. So yes, this part works. And then let's try a 1 because we are over here. So 1 squared plus 6 times 1 plus 5, is that greater than or equal to 0? Well, everything's positive, so yes, it's going to be greater than or equal to 0. Okay, so we need from negative infinity to a negative 5, but we need the negative 5 in brackets because remember it's a less than or equal to, so negative infinity to negative 5 in union with our negative 1, which is in a bracket, to infinity because both of those sections work. So it's letter D is the solution for that one. All right, didn't quite give us enough space, but that is the solution. Let's take a look at number 3 as just to do another one. Express the solution to the inequality x to the third plus 7x squared, which is less than x plus 7 in interval notation. Okay. Moving everything to the right side or the left side of the equal sign gives us, I'm going to save myself some space here, x to the third plus 7x squared minus x minus 7 is less than 0. I'm going to factor by grouping, and that's this group plus this group, okay? In this group, I can take out an x squared, and that leaves me with x plus 7. In this group, I can take out a negative 1, which leaves me with an x plus 7. So my x plus 7 is what they have in common now, and that leaves an x squared minus 1, which all of this is less than 0 or equal to 0, however you want to think about it. This is further factorable. So my x plus 7, and then this factors to an x plus 1, x minus 1, right? It's a perfect square binomial, and it turns into a sum and difference binomial. Setting all of those equal to 0, we see x is equal to negative 7, x is equal to negative 1, and x is equal to 1, positive 1, okay? All right, number line. Here's our number line. We have negative 7, negative 1, and positive 1. All right, so let's test out the different parts. Testing out our parts, I guess we're going to start with negative 8, right? So negative 8 cubed plus 7 times negative 8 squared. I'm going to be working right here. Minus 8 minus 7. Is that less than 0? That is my question, right? Well, let's look at what negative 8 cubed is. That's a pretty huge number. So 64 times 8 is 512, and it's going to be negative. 7 times positive 64, because negative 8, the quantity squared, is positive 64. So that's going to be plus 448, minus 8 minus 7. So 448 minus 512 is negative. That's already negative. So yes, this is less than 0. So yes, this works. Okay. Our next interval is between negative 7 and negative 1. I'm going to choose a negative 2. So negative 2, the quantity cubed, plus 7 times negative 2, the quantity squared, minus 2. Oh, so that should have been minus minus 8. I don't know that that would make a difference. This should have become a plus 8 because it would have been minus minus 8. So that becomes a plus 8, which makes this just a positive 1. No, it's not enough to make a difference, so it still works. Okay, minus minus 2, and then minus 7 less than 0. This becomes a plus 2. Negative 2, the quantity cubed, is a positive 8. Is a negative 8. Geez. Negative 2 squared is a positive 4 times 7. Gives me a positive 28. So 28 minus 8 plus 2 minus 7 is a positive 15. So that is greater than 0. So this part doesn't work. All right, so they don't give us a lot of room, but this is definitely takes some work, okay? Between negative 1 and 1 is a 0. Perfect. That ends up being is 7, negative 7 less than 0. Because if I put a 0 in, this is a 0, this is 0, this becomes a 0. I got negative 7 less than 0. Check. Yes, that's good. Now, let's do a positive 2. So I have positive 2, the quantity cubed, plus 7 times a positive 2 squared, minus positive 2 minus 7. So here we have 8. This is 28, and that's enough. I don't need to finish it, right? I'm just trying to find out, is it going to be less than 0? And no, it won't be, because these are already too big for that to make a difference. So no, this part doesn't work. Okay, so we have the interval from infinity, which is going to be in parentheses. So we're already either in A or B. Infinity to negative 7, and it's going to be in parentheses because this was a less than symbol. So I'm pretty sure we're at part A, and that's going to be in union with the negative 1 to 1, both in parentheses. So it's letter A. All right, these aren't super hard, but they do take up some time and more space than was provided. So you might need scratch paper, though some of these give us plenty of space, right? Let's take a look at one of these story problems, and then we're going to do some of the fractional ones over here, okay? So let's take a look at number 5.4. A ball is thrown straight up from the top of a tower that is 280 feet high, with an initial velocity of 48 feet per second. The height of the object can be modeled by the equation s of t equals negative 16t squared plus 48t plus 280. Express the times that the ball is lower than the height of the building in interval notation. So now we want it to be less than the height of the building. So we have negative 16t squared plus 48t plus 280 has to be less than, it doesn't say and equal to, it just says lower than the height of the building, so less than 280 feet, because that's how high the building is. When we subtract 280 from both sides, we just get negative 16t squared plus 48t being less than 0. Okay, that's our initial thing that we're working with here. So now we need to factor, and we're going to factor out a negative 16t. And that's going to leave behind a positive t. And 16 goes into 48 3 times, so t plus 3 less than 0. So t is going to be 0. Remember, when it's outside the parentheses like this, just multiplied, it's always 0. And this t is going to be equal to negative 3. All right, setting up our number line. We have 0 and we have negative 3. Okay, so we have 3 parts. Testing a piece over here, remember we're going to test into this equation because it's just going to be easier. So we're going to have a negative 16 times t squared. Let's choose a 4, negative 4, I guess. So negative 4 squared plus 48 times a negative 4. Now, I'm not even going to solve because even though this becomes a positive 8, it's still being multiplied by a negative 16. This is also going to be a negative number. It's definitely going to be less than 0. Check. Okay? this space here, I'm going to choose a -1. So I have -16 times a -1, the quantity squared, plus 48 times a -1. Again, this is a negative number, this is a negative number. We're trying to see, is it going to be less than 0? Yes, it's going to be less than 0. Now, what about over here? Let's just try a positive one. -16 times 1 squared plus 48 times +1. Is that less than 0? Well, this is just going to be a -16. This is going to be a +48. No, it is not less than 0. So to express this in interval notation, we need all of this chunk over here. So we need parenthesis, and I am not good at drawing the symbol, but infinity symbol, comma, 0. Okay, so anytime our time is what seems to be negative, right, under the building, that's what we're looking for. And so that's what we end up with, infinity, comma, 0. I need to make a quick correction because this right here should have been a -3, which would have made this positive. Okay, so this shouldn't exist. And it should be, this section still doesn't work, but it should be a 3 here. That's not correct. Of course, the ball in negative time is below the height of the building, right? But let's check over here where the ball in this section. So if I have -16, and I'm going back to here, right? And I wrote a parentheses. Geesh, where is my head at? -16, and we're going to choose 4. Okay, times 4, the quantity squared, plus 48 times 3, or times 4, goodness gracious, is that less than 0? Well, 4 squared is 16, so 16 times 16 is equal to a -256. 48 times 4 is equal to a +192. So yes, this would be less than 0. So this is the section that we actually care about. And it's going to be from 3 seconds to infinity. Okay. Got to watch our signs. Everybody makes mistakes, but we need to make sure we check our work to see if these things make sense. All right. So that is a correction to this problem. Let's take a look at 5.7, some of these fractional ones. Express the solution to the inequality 1 over the quantity x squared plus 2x minus 3 is less than or equal to 0 in interval notation. Okay, again, not really giving us a lot of space. 1, I mean, the numerator is just finished already, so we really just have one problem to deal with, or one problem to set up, which is x squared plus 2x minus 3 less than or equal to 0. So what factors multiply to give me a -3 but add up to give me a +2? Well, that's going to be x plus 3 times x minus 1 less than or equal to 0. So x is going to be a -3 and x is going to be a +1. All right, so we've got -3 and we have +1, and we need to find the spaces in between. Okay, so is 1 over, okay, 1 over, let's choose a -4, sorry. -4 plus 2 times a -4 minus 3, is that less than or equal to 0? Okay, well, that's this interval here. This is going to be a +8 minus 8, so it's going to be a -1/3. -1/3 is less than or equal to 0, so yes. This space here, I'm going to choose a 0. And when we choose a 0, this becomes 0, this becomes 0. And then I have, again, a -1/3. So yes, that space works. Then over here, let's choose a 2. So 1 over 2 squared plus 2 times 2 minus 3. 4 plus 4 is 8, minus 3 is 5, 1/5 is greater than 0, so this does not work. Okay, so we have a less than or equal to, it's going to be negative infinity. Oh, that's what this one needed, was a negative infinity. Okay, negative infinity, comma, 1. And the 1, oh no, because the 1 was in the denominator. The 1 was in the denominator, so it still gets a parenthesis. Because remember, answers from your denominator are always going to be parentheses. So a negative infinity, comma, 1. And I must have made an error. Let me check. All right, so I didn't make a mathematical error, but I do see my error because this negative 3 cannot be included. Just like this, I wasn't putting my brackets on my number line. So this is going to be negative infinity, comma, negative 3, both in brackets, in union with negative 3, comma, negative 1. That's how it's going to be written, because we have to skip this negative 3. Where in the other ones, it could be included because they weren't denominators, right? Some of the pieces anyway could be included. But this one we definitely have to skip these because they were in the denominator. So that is still not an answer that is here. I chose 0, which is between negative 3 and 1. This becomes a 0, this becomes 0. That's a negative 1/3. This section does work. I figured out where my error is. Okay. Negative 4, the quantity squared, is positive 16. 2 times negative 4 is a negative 8 minus 3. This would actually be positive, so that section does not work. So this section does not work, and it's just this section in parentheses. Oh my gosh, crazy. Okay, I got to focus here. All right, so that's where my mathematical error was. This section is not included. It's only this section. This is our answer part, which is answer A. All right, sorry about that. You know, we're only human, right? But we definitely need to check our work, okay? So sometimes this multiple choice is kind of nice. It helps us to check our work. But let's take a look at another problem here. Do number 5.8. Express the solution to the inequality x over the quantity x squared minus 16 greater than 0 in interval notation. 2 parts. X is, let's just say, equal to 0, and x squared minus 16, which are perfect square binomials, so it's going to factor 2. X minus 4, x plus 4 is equal to 0. So again, x equals 0, x equals 4, and x equals negative 4. Setting up our number line, we have negative 4, 0, and positive 4. So we have 1, 2, 3, 4 sections that we have to check. All right. So remember that this negative 4 and this positive 4 have the parentheses. So they are not included. They cannot be included. And honestly, the 0 has the parentheses too because it's greater than 0. Okay, so I wasn't marking the lines before, but that was a mistake. So we need to start marking our lines. So let's take a look here at negative 5. So is negative 5 over the quantity negative 5 squared minus 16 greater than 0? Well, this becomes a positive 25, so the denominator is positive, but the numerator still makes the whole thing positive, so no, it is not greater than 0. Let's try a negative 1. Is negative 1 over negative 1, the quantity squared, minus 16, is that greater than 0? Well, again, this becomes a positive 1, but so this is now a negative 16, but I have a negative over a negative, which becomes a positive. So it's 1 over 15, which is greater than 0. So check. Let's try a positive 1. So I have 1 over the quantity 1 minus, or 1 squared minus 16. So now this is a negative 1/15. So no. And let's try greater than 4. So a positive 5 over positive 5 squared minus 16. 25 minus 16 is a positive, so this is greater than 0. Check. So those are my two sections. So how do I write this? I'm going to write it as negative 4 comma 0, both in parentheses, unioned with positive 4 comma infinity. All right, so let's see where that is over here. I believe it's this one here, negative 4 comma 0, union with 4 comma infinity, letter D is our answer. All right? Go ahead and finish the rest of these problems on your own, and then we will move on to the next part of this section. On page 76, we start with the greatest integer function, okay? It's also referred to as the step function, which it says right here. It's also referred to as a step function, and it's written like this. F of x is equal to brackets with, in this case, an x on the inside. The greatest integer of any value of x is the integer, because remember, we're talking about integers. It's an integer function, is the integer that is less than or equal to that of x, or the integer to the left of x on the number line. So you don't need to draw a number line, but if you can visualize it, that will help you. So for example, the greatest integer of 2.5 is equal to 2. Okay? Think of that number line. We're going to the left of there. The greatest integer of negative 2.5 is negative 3. And then any integer is its own greatest integer. So if you're finding the greatest integer of 2, the answer is 2. So you might think, oh, we're rounding down. Yes and no, right? If it's positive, yes, technically you're rounding down. But when it's negative, you're technically rounding down, as negative 3 is smaller than negative 2, but most people wouldn't think of it that way. So just think of it as falling to the left till you hit the first whole integer, whole number, okay? It says, notice multiple input values will give the same output. For example, if x is in the interval between 0 and 1, then, or that is 0 is less than or equal to x, which is less than 1, then the greatest integer, or the step, is at 0. All of the things, all of the decimals places between 0 and 1 have the greatest integer of 0. And when you graph it, it looks like this, where the integer to the left is a filled in circle, but the integer on the right is an open circle, because it's not included in this step. This negative x equals negative 1 is included on the next step, and so on and so forth. And it literally looks like steps. That's why they usually call it the step function. Okay? Taking a look at how you do these. Example 1 on page 77. Draw the graph of the function f of x equals the step of x plus x. All right. Really the only safe way or easy way or way to do this is to set up a little chart, our XY chart, right? And they have put in the intervals in which they're working with, you can just use, well, I mean, you can put in regular numbers and try to graph those, but remember, it's always a section. So, and the one on the left is always going to be included, while the one on the right is not. So, between negative 2 and negative 1, the step is at negative 2, so then it's negative 2 plus x, and so it goes on this like little slanty bit, right? But remember, x is in between here is never going to be greater than 1, so it makes this slanty bit. So then the next step is starts at negative 1 and it open circles at 0, okay? But remember, you're always adding whatever x was. So in between here, say x was a negative 0.5, right? It's always going to be going on a slant for this particular type of problem, for this particular setup. All right, looking at the next example. Draw the graph of the function f of x equals the greatest integer, or the step 2x, okay? Choosing their integers, their integer interval, and they've gone by half steps because of the 2. It just makes it easier. So, because remember, you're going to be multiplying it by 2, so really it should be 1/2. We'll make it an even step. You don't want to, that's the issue with the step function, the integer function, the greatest integer function, is you could easily overstep, and then your numbers aren't going to work out correctly. So we have to find that middle ground. And so for this one, it's 1/2, right? X is being multiplied by 2. To cancel that out, we would multiply by the reciprocal, which is 1/2, which is what they've done here with choosing their steps, okay? So they've gone from -1 to a -1/2, all right? When you're in between there, the -1 to 1/2, that's all going to be times 2, and then fall back, so the function is at -2. -1 to 0 times 2, drop back is a -1. 0 to 1/2 times 2 is going to drop back to the 0, because 0 and anything greater than 0 but less than 1 is 0 for that step function, okay? So even though this is at, if you put in a 1/2, right, you'd get a 1, it drops back. Well, you can't get a 1 exactly, but it drops back to 0, okay? Because remember, 1/2 is not included, so you technically can't get all the way to 1/2. It'd be something minutely smaller than that. Anyway, it sets up this level of steps, very small, choppy little steps, right? Okay. You might be thinking, wow, what the heck? But let's just do some of these together, and we'll completely understand it. We'll get it by the time we're done, okay? 511, because that's it. This is it for this section. That's the step function in a nutshell, okay? 511, evaluate f of x equals the step of x over 3 for x equals 2. That's it. They only want you to do it for that one part. So we have the step of 2 over 3, 2/3. What is that going to drop back to? Remember, we think of it on a number line. What is it going to drop back? What is the integer that it's going to drop back to? Well, it's not even 1, so the integer is 0. Letter A. It's going to drop back to 0. Okay? Let's turn the page. We're going to do a couple of these together, and then we're going to do number 16. It says, choose the graph of the function f of x equals the quantity, or 2 times the greatest integer x, or the step of x. Okay? So now, the step of x by itself is always just going to be an integer, right? It's always going to be 0, 1, 2, 3, 4, because everything to the right of there, but we're doubling it. So we're actually taking 2 steps for every one. And that's what this is going to look like, right? We're going 1 step to the right, and then we're taking 2 steps up. And that's what is represented here. 1 step to the right, 2 steps up. 1 step to the right, 2 steps up. Okay? So the answer is D. Or I guess they want a check mark. 513 says, choose the graph of the function f of x equals the step of x plus 1. So remember, the step of x is always going to be 0, 1, 2, 3, right? And this is just a plus 1. So really, it's going to look like the normal step, except for the point you're at is actually 1 point higher than, does that make sense? I mean, it's all going to look the same, exactly the same. this plus 1 kind of gets lost in the graph. Okay, looking at this, you wouldn't necessarily know the plus 1 is there, except for the fact that this point should be at the origin. That's the only way to know the plus 1 is there, is because this solid point should be at the origin and then move over. That's where the steps should be. So these are kind of pushed back, right? Instead of this step being at the origin, it's pushed back 1. And that's what that plus 1 did. And so that's letter A. All right, you take a look at the last two. We're going to look over here at this problem 16. Looking at problem 516, it says draw the graph of the function f of x equals the step of x squared. Now, because there's an x squared here, it's definitely going to mess some things up. So I know the book had us drawing intervals, right? But I don't think that's going to help us here. And honestly, it doesn't really go into depth on how to choose which intervals, you know, like where to start with your intervals. So here is how I know and understand how to do this type of problem. And it is a little tedious, but we will get it sorted out. Okay. So we're talking about x squareds, right? Let's start with, I'm trying to think of the best place to begin here. Let's start at -2. -2, the quantity squared, is 4, right? The step of 4 is 4. Then let's do -1.9. And this is very tedious, right? But this is how we're doing it. So because I know that the negative is going to square out, I'm just going to do 1.9 squared and see that that is at 3. I want this to be somewhere. I don't have to move it all the time. 3.61. So its step is at 3. So right there, that difference puts them in a different step, right? They're already at a different step. What about 1.8 squared? 3.24. So -1.8 squared is at, actually, you know, these would be plus or minus, because that's how that works. That's how we're doing it, right? Is at 3.24. So that step would be 3. All right. I gotta, here, what if I move my book? There we go. Okay. What about our plus or minus 1.7? Okay. So 1.7 squared is 2. All right. So we're already out of that step 3 and we are at 2.89. So that step is at 2, right? Plus or minus 1.6. Quantity squared is at 2.56, so that's at 2. Plus or minus 1.5 is at 2.25, so that's at 2. Plus or minus 1.4, and I know this is tedious. It's just what it is, okay? You can't really, as you can see, you couldn't have chosen the interval between -2 and -1, because look at all the different steps that fall in between there. That's what I'm saying. With these step problems, you have to be careful to figure out when you're taking the next step. It's not always just a blank one thing. We're squaring it here. That changes our problem quite a bit. So we're on 1.4. Quantity squared is at 1.96. Okay. 1.96 is a 1. We step to the 1. Plus or minus 1.3 squared is 1.69. Again, that's a 1. Plus or minus 1.2 squared is at 1.44, which is a 1. Plus or minus 1.1. And you might be wondering, why did we just not start with 1? Because this is a lot. The reason I didn't start with 1 is because plus or minus 1 squared is just a 1, right? And 1 is 1 is 1. And you can see I've got a big chunk of 1s here. So everything between plus or minus 1 to plus or minus 1.4 is a 1. But what about in between? Well, 0 squared, right? I'm going to take a jump here just real quick. 0 squared is 0. And so there is no falling back to anything else. So if we did 0.9 squared, that's going to be a 0, okay? So 0.5 squared is going to be a 0. All of these are going to be less now than 1. That makes them a 0. So I could say with confidence that anything less than -1 through less than +1 is a 0, right? So 0.8 is a 0, 0.7 is a 0. All of these numbers are less than 1, so that would make them a 0. So that interval I could choose. Then looking at our problem here, okay, I'm going to draw a line right here. I can say anything, let's see, between a -1.4 and a -1 where the -1 is included, right? That's this interval, is going to be a 1. But now I need to do the positive part, which tells me that 1 through +1.4 is a 1. Although I feel like this 1.4 could be included. Same with the negative here. Okay. But we have to think about the transition, like the 1.49 is already a 2, 1.45. See, I mean, these problems can get a little bit tricky. 1.45 is a 2, so we would have to probably leave this as a parenthesis and leave this as a parenthesis, because not all the 1.4s, 1.44 is still a 2, 1.43 is still a 2, 1.42. So 1.41 drops us back, right? But we don't need to go to that. Let's not go that far. All right, looking at our section of 2's. Okay, we know that we can start at, let's see, a -1.7, comma, -1.5, and all of those are going to be 2. Also, my 2's are going to be, remember, because we have to write them in a different order, which is kind of messing me up a little bit, 1.5 through 1.7. Those are all 2's, okay? And then I have a very small section of 3's, and that is going to be at -1.9, oh, that's a bracket, comma, -1.8, and that is a 3, and let's see here, it's going to be a +1.8, comma, 1.9 bracket, which is also a 3. Okay, that's as far as I'm going to go. I'm not going to continue to figure out the interval of the 2. We'd have to do more, and we've already done a lot. All right, so let me get my graph ready, and we'll graph it. So the book was just quick to give us the intervals. I know you're thinking this was a lot more work than they did, and it is, because the book gave us the intervals, and they gave us the answers. But they didn't actually tell us how they found the intervals, and this is tried and true, really the only way to do that. And I know it's a lot of work, but the calculations are not really that hard. We did on our calculator super quick. Setting these up was a little bit more challenging, right? Because we got to think, okay, where does this fall and this fall? Here's my graph. I know between -1 and +1, neither of those included, mind you, our answer is 0. So open circle, this graph is so tiny, and there's our step, right? Okay. Then from -1 solid to a -1.4, which is like right here. Okay. This is a very tiny graph. We have a 1. And then the same on the opposite direction, right? Solid dot here to the 1.4, which is an open circle. And that's our next step. Then our step goes from a negative, we're at a 2 this time, a -0.5. So we'll just put a solid dot here. So remember, when you're taking your steps, this step was open. So the next step needs to be solid, right? That's how this works. So I have a solid dot here at -0.5, and it goes to 0.7. Oh my gosh, I don't know how they expect us to actually draw this. -0.5, -7. Just do your best. You know, I'm not giving anybody fails because it's hard to read when this is just hard to read. And our last one is 3, which is at 0.8 to 0.9, which are basically right next to each other. 0.8 to 0.9 and solid. So very tight little steps, and I would assume they only get smaller as it goes up, because x squared is an exponential function, right? So there's our graph. I guess I could have done 4 blocks equals 1, you know, every 2 steps is 1. You can do that on your tests or your homework, right? Make 2 blocks 1 step, or 3 or 4 blocks 1 step, just to spread it out a little bit because it's very compact. But seeing as how the book didn't walk us through finding the intervals, this is the way that we find our intervals. For the square, it worked out, honestly, even though this was a lot of work, fairly easily, because it was just a plus or minus, right? We only had to do the process 1 time, and we got 2 answers. All right? Okay. Take a breath, finish the rest of the problems that we didn't do, and then meet me back here for the next part of this section. Okay, on page 80, we're going to start talking about exponential functions. And it says a function in which the independent variable appears as an exponent is called an exponential function. So I was calling the x squared exponential function. It's not really. It just rose exponentially, which is why I was saying that, because it's going to go on this tight curve and really shoot up really fast, right? Because it's a square. But here's what an exponential function looks like. B times a to the x power, or f of x equals 2 to the x, or f of x equals 3. And so in this equation, 3 is the b, right? A is the 4, and then x is, of course. Or we could have f of x is equal to 5 to the power of x squared, okay, which is like a double-double, right? And it says to graph these, the only really way, just like in the last section, is to make a table and find the corresponding values, right? Straight to the point. Let's make a table, find the corresponding values. Draw the graph of the function f of x is equal to 2 to the x power. Well, if my x is a -2, so I have 2 to the -2 power, then my f of x is 1/4. If my x is a -1, I have 2 to the -1 power, which is a 1/2. Remember, when you have a base to a negative exponent, right, you have to think of it like a fraction. It's going to cross the line and change its sign. So it becomes 1/2 squared to the +2 power then, or 1/4, okay? If it is 2 to the 0 power, the answer is 1. Any number to the 0 power is always 1. 2 to the 1 power is 2. 2 squared is 4, and so on. It's going to shoot up pretty quickly. Plot your points, and you're done. All right? So, top of page 81, column 1, example. Draw the graph of f of x equals 2 to the -x power. Okay, so they've chosen the same set of numbers, which is fine. But this time, remember, we're going to have 2 to the -2, right? And we can't have minus minus in math. It becomes a plus. So 2 to the squared is 4. Okay, 2 to the negative 1 power is 2, and so on. It's just reverse of the last one. Again, plot your points. We put an arrow at both sides because this continues on and on forever. Amen. All right? This will constantly get closer and closer to 0, but never actually get there. All right. The Euler constant. And most of the exponential functions you'll see in this unit, the base of the exponent, the a, in the exponential function is a positive integer. The exception to this is the Neperian logarithm base number e. This is an irrational number which approximately equals 2.71828. It goes on and on and on. It's used for calculating growth and radioactive decay, all right, among other things. On your calculator, let me grab mine again. On your calculator should be an e to the x button or an e button of some sort. My regular e is way down here. It's a little red button. My e to the x, or e to an exponential on this calculator anyway, is here, e, and it's got like a little box up there. If you are sporting, sorry, it's dusty because the Texas Instrument is not my favorite. If you are sporting a Texas Instrument, though, no shade, but my e to the x for the Texas Instrument is right here, e to the x, okay? So it's still a second function. Looking at an example up here. Draw the graph of the function f of x equals e to the x, okay? Remember, now we still have our x values going in. So let's turn this on. We have my e to the x is here. So I'm shifting, pulling up my e to the x. E to what value of x? I am doing a -2 to start, equals 1.35. They've rounded it to 1.4. All right, let's do, they've done it for you. I'm just showing you how to do it on your calculator, okay? Shift, my e to the x is now a -1. Make sure you close your parentheses. It's important. 0.367, so 0.37. All right. Let me do a couple on this Texas Instrument for those of you with one of those. Clear. Let's do e to the 0 power. Okay. Where did I say it was? Oh, here. Okay. So second e. So it comes up exactly the same. 0. Close your parentheses. And hit enter, so it's 1, all right? E to the 1 power, so second e to the 1 power, close my parentheses, equals 2.718. We are rounding it to 2.72, and so on and so forth, all right? Now it says here that if you look at the graph of e to the -x, all it has is flipped it. Right on this point right here, the y-axis, they've flipped it. It's like the mirror point. All right. And down to the bottom of the page, it says the most effective way to graph an exponential function is to calculate several values in a table, which is what they have done for us, but what we will do going forward. All right, let's turn the page and look at some of these. We are at the top of page 82, looking at problem number 17. Which of the following is or are an exponential function? Remember, an exponential function is a function in which the exponent is a variable, which is c and d. All right. Choose the graph number 18 for the function f of x is equal to 3 to the x power. Okay. First things first, we know that if x is 0, then the function is 1. So looking at these, all of them are at the 1. So they're really trying to make us work here, okay? So we don't have any that we can cancel out. But we also know that 3 to the 1 power, or if when x is 1, 3 to the 1 power is 3. So which graph shows us x is 1 and our function is at 3 is letter A. We're just going to double check to make sure. 1, 1, 2, 3. No, not quite there. 1, and that one stops at 2. So our answer is A. There's a whole bunch of these graphs to work through. I'm going to let you do that, but we're going to turn to page 84 because there's an actual problem that we can work through together there. All right, looking at page 84, it says draw the graph of the function f of x equals e to the 1 over x power. So we're going to make our chart, and we're going to choose some values for x, right? So -2, -1, we're just keeping it simple, 1 and 2, all right? When x is -2, I have e to the -1/2. So how I'm going to put that in my calculator is I'm going to pull up my e. I hope you can see this. Yep. And it's going to be to the -0.5 power. Now you can put a fraction in. I know some people's calculators have those nice little fraction things. You know, I got one right here. I just don't feel like using it. So 0.5 is good enough. My answer is 0.606. So I'm going to round my 0 based on a 6, so 0.61. Then we do the next one, right? I have e to the -1, right? Because this would be 1 over -1, which is just to the -1 power, which gives me 0.36. So sorry about the interruption there. E to the -1 is 0.367 or 0.37. Next, e to the 1 over 0. Well, 1 over 0 is undefined, and we can't really have e to the undefined problem, right? So when it's 0, it is undefined, all right? Now, what about 1? E to the +1. So shift e, +1, close my parentheses, equals 2.718 or 2.72. And then I have e to the 2 power is 7.389 or 7.39 is what we're going to put, okay? Now, what's kind of strange about this is the way these points are set up. So we're going to start to plot these. When x is -2, I have my y or my function at 0.6, which is, we're just going to estimate maybe right here. When it's at -1, it's at 0.37, so a little bit less. I have an open circle here. Then when my x is at 1, my value is 2.27. So when I'm at 1, I'm almost at 3. And when I am at 2, I am at 7.39. 2, 1, 2, 3, 4, 5, 6, 7.39 would be right about here, okay? So these points, if you look at them, they don't really line up. So this graph actually kind of looks like this. And the book answer key is not correct. I don't really know. I feel like it would be a swoopish, probably more like this. Probably more like swoopy like that, and it's going to go up like that. Okay? Because it's a fraction, right? This is an undefined point. It kind of bends and twists our graph. It kind of floats in two different directions. Some graphs are like that. Some graphs are kind of weird. Okay? All right, finish identifying these other graphs here, and then meet me back here for the next section. On page 85, we are talking about logarithmic functions, okay? The inverse of an exponential function is a logarithmic function. Remember that to find the inverse of a function, you must interchange the range and the domain sets. So an exponential function is y equals 10 to the x. The inverse would be x equals 10 to the y. The problem is we can't solve for y as an exponent, right? Because remember, it's the dependent value. It's dependent on x. And so to do that, we have to make it a log. So y equals log base 10 of x is the same thing that's written here, okay? but we've written it in logarithmic function. So the base is always the base of the exponential function, and the logarithm y is the exponent. So if you have f of x equals 6x, then the inverse is the log base 6 of x, right? That's how you write it, log base 6 of x. So it says over here, consider the function f of x equals 10 to the x. Its inverse would be log base 10 of x. If you solved for some points, you can see that they are opposite of each other, right? So if g of x is 2 to the x, then the inverse of g of x is the log base 2 of x. In general, if f of x equals b to the x, then the inverse is the log base b of x. Okay? The example here. Find the inverse of x for f of x equals 3 to the x plus 1 power, right? The quantity x plus 1 power. They say start by interchanging it, but we already know that this is going to be our log base. So log base 3, and the x plus 1 is going to be sitting right here, okay? Sitting out next to it is what we're looking for. So y equals log base 3 of x minus 1. I would probably put this in parentheses so we don't confuse this minus 1 as just being an add-on, right? But that would be our inverse. I mean, you can swap them out or whatever, but this is, right? Because that's what they kind of done here. Oh, because that's how they went from a positive to a negative. So it is a little bit different. All right, hold on. Let's take a look at that again. They've swapped it out. The x, just the x and the y. I was starting thinking of this whole thing in parentheses as being our x, right? But it's not. They've swapped it out for the actual just x. This became a y. Therefore, y plus 1 is equal log base 3 of x. And then to get y by itself, they had to subtract 1. And that's the inverse, okay? So be careful if there is more than one term up here that we handle it properly. All right, let's turn the page. Shifting the logarithmic function, okay? Logarithmic functions have two key features. And here is like the general form where it's f of x equals log base b of the quantity x minus h plus v, all right? So they have two key features. The point at which the logarithm section of the function is equal to 0 and the vertical asymptote. Okay, remember an asymptote is a line that or is it like an invisible line? I usually use a dotted line that your graph approaches but never crosses, right? So do you see these features here in this equation? Well, it says it turns out the logarithm section of the function will equal 0 when the expression contained by the logarithm is equal to 1, when this is equal to 1. So it says makes sense because you know that b to the 0 power is equal to 1, right? That is very true. Any number raised to the 0 power is 1. And it doesn't matter what that number is. So this point occurs when x minus h is equal to 1, or when x is equal to 1 plus h. So we can solve this for 1, excuse me, to find out when our equation will be at 0. So if h is equal to 0, this point will be at x equals 1. So when a non-zero h will shift the function horizontally from side to side. Okay? If h is a positive number, I'm adding. This number is going to get larger. We should be moving to the right. If h is a negative number, right, then this technically becomes positive here, and I'm subtracting it, and it should move to the left. All right? They want us to look at this form, k equals b to the y, right? I'm not sure why we're doing k now instead of x, but that's besides the point. It says if b is a positive number, but k is negative, there's no possible value of y that can make this situation true. We can't raise something to a power and have it be a negative answer. Thus, the h, which again we're talking about up here, also shifts the vertical asymptote. Remember, that's that imaginary line that we approach but never cross, from x equals 0 to x equals h. All right, and then it says here, well, what about the v? Well, remember the v was up here at the end. It's plus v, right? So what about the v? If the v is equal to 0, or is just not there, right, then the 0, or where the function equals 0, is going to be at 1 plus h, which we just talked about up here, right? 1 plus h, comma 0, because we don't have a v. But if v does not equal 0, this point moves to 1 plus h, comma v, positive or negative. So a non-zero v shifts the function vertically, up or down. All right. Now, reflections, so the v moves us up and down, the h moves us left and right. Reflections and dilations of the logarithmic function can be achieved by multiplying the base of the function by a constant. So now we're multiplying, okay, and that's going to cause a reflection or a dilation. G of x is equal to a log b of x. How will the graph of this function be different from f of x equals log base b of x? So they said test it out, and that's what they're doing here. So remember, our g of x is a times the log of b, log base b of x, and our f of x is log base b of x. So here's the general log base b, and here is the technically 2 times, right? Because here's our b, a log base 10. Not sure why they didn't just write it that way. And the a is 2. So they're doubling it basically. And you can see that reflected here. So it's twice the size, right? So the points are farther away than these points were. So it's going to change the look of the graph, right? It says another modification we can make is to the base of a function is to multiply the inside of the logarithm by a constant. So here we have g of x is equal to log base b of the quantity c times x. All right, and so that's this next example here at the top of page 87, where my b is still a base 10 and my c this time is still a 2. Last time a was a 2, this time c is a 2. And they've chosen some more points. I'm going to ignore the 1/2 for now. So if we have log base 10 of 2 of 1, it's going to be 0. Remember, our regular f of x is just the normal log. But log base 10 of 2, because this would be 1 right here, 1 times 2 is this, right? So we've shifted over. Where we should have been at 0 back here, we've shifted over a point or half a point, or however that works out to be exact here, 1 point, right? We've shifted over. Although we kind of skipped this 3 point here. I don't see a 4 point whatever, right? Because these here match, here match. I wonder, you'd probably have 2.5 would match. Then our 3 would match, you know. So it looks like it's about a half a point shift, right? So it's shifted to the right, all right? For the next example, it says, describe the transformations that take place on the graph of the parent function f of x equals log base 10 of x to produce the graph function g of x equals log base 10 times a quantity negative 3x minus 6 plus 2. First, you have to factor the expression, since they have a factor in common, inside of the parentheses, and you end up with this. So now here is our g of x, which is here. The f of x is over here. So they're saying, what is the difference? Well, this negative 3 is what causes us to be reflected across the y-axis, okay? And so that's what it says. You can see that the function has been reflected across the y-axis. Even if this drawing wasn't here, though, the negative 3 would have us being reflected across the y-axis, right? It's horizontally compressed by a factor of 3, right? So the swoop here, the arch is compressed. and it is shifted 2 units to the left because the h is a -2. Okay, so in this thing, remember x minus h equals 1 or whatever. Well, equals 1. So my h in this term, or sorry, I'm not worried about the -1 part right now, but in the main equation, which is here, right? X minus h is how we move things plus v. So my h has to be a -2 to make this be a positive, right? So my h is -2, so that tells me I move 2 units to the left. And then my v is a +2, so it's 2 units up. All right. Now, in the homework, I don't know that they actually give you the graphs, but we'll see in a minute because the homework is right here. So looking at problem 527, what is the inverse of the function f of x equals 6 to the x power? Well, remember, it's going to be the log, and the base is 6, because that's the base here, to the x power, which is letter A. Okay, so that's how we switch back and forth. We write the word log, the base here is our 6, and the x just sits right there. All right, and that's the inverse. Okay, let's turn the page. Looking at problem 28, what is the inverse of the function f of x equals 3 to the quantity x minus 1? Now, this one's a little bit different. So we're going to write x equals 3 to the y minus 1, right? Which can be changed to x equals log base 3 of y minus 1. Looking at problem 28 at the top of page 88, we have what is the inverse of the function f of x equals 3 to the x plus 1? Well, we can rewrite that as x equals 3 to the y minus, sorry, it's minus 1, y minus 1. And then when we rewrite that, we're going to have y minus 1 is equal to log base 3, okay, there's my base, of x. Now I could solve by adding a 1 to both sides, and so I get y is equal to log base 3 of x plus 1, okay? Log base 3 of x plus 1, which is letter B. All right, let's do another one. What is the inverse of the function g of x equals e to the x? All right, well, we can think of this just like the other one. It's going to be log base e of x. So that's A. All right, I'll give you a couple of those to solve on your own. Let's take a look at problem 32. What is the inverse of the function h of x equals log base 7 of x plus 3? In parentheses, so that gives us a hint. So we're going to write it as x equals the log base 7 of y plus 3, and now we're going to change it over. So my y plus 3 is going to move to the other side of the equal sign, okay? And then my base comes up, so 7 is my base, and it's to the x power. So that is the inverse of our h of x, okay? Now it says, which of the following points lie on the graph of the inverse of the function f of x equals 6 to the x plus 1 power? Well, the inverse is going to be written as x equals 6 to the y plus 1 power, right? We're not going to bother changing it to log right now because we can try and solve from here. They've given us a choice of answers, right? So we'll start with the first one. Is -1 equal to 6 to the 0 plus 1 power, right? Well, 6 to the 0 plus 1 is 6 to the 1 power, which is 6, so no, that doesn't work. Is -1 equal to 6 to the 1 plus 1 power? Well, that's 6 squared, so nope. Is +1 equal to 6 to the -1 plus 1 power? Well, -1 plus 1 is 0. 6 to the 0 power is 1, so yes, it is this C, 1, -1. Okay? I'm going to jump over here to problem number 36. For problem number 36, it says draw the graphs of the following function and its inverse. So first they want us to graph f of x equals e of x, and then they want the inverse of that, right? So first of all, let's find the inverse. And that's going to be the log base e of x, all right? We're going to set up our chart, but I'm going to have two parts. I'm going to have my f of x, and I'm going to have my f of negative x, or inverse f of x, okay? And so let's plot some points. Let's plot the points -2, -1, 0, 1, and 2, just to make it straightforward. We got to grab our calculator, and I'm going to put it where it's going to be seen. Okay, right there looks good. Okay. So remember, our f of x is e to the x. So we want shift e to the x, and we're starting with -2. Close your parentheses, equals 0.135. So I'm going to put 0.14. All right, so if our f of x is at the point -2, 0.14, then our inverse, remember, the points are switched. So this is going to be at 0.14, -2. And so for our f of x is e to the -1 power. So let's do shift e to the -1 is 0.3678, so 0.37. So its point here is going to be at 0.37, -1. What about 0? So shift e to the 0 power, close your parentheses, is 1. That means the inverse of it is going to be at 1, 0. All right, remember the inverse is switched, is the points are opposite. You swap the x and y, right? That's how you find an inverse. So what about the e to the 1 power? It is 2.718, or so 2.72. So this is 2.72, 1. And the last one I want to look at is e to the 2nd power, or squared, which is 7.39. So this point is at 7.39, 2. Let's get our graph set up. All right, let's take a look here. Let's graph our f of x first. So at -2, we are at 0.14, which is real low, like right there-ish. -1, we're at 0.37, barely more than that. At 0, we are at 1. Okay. At 1, we are 2.72, which is almost 3. And at 2, we are at 7.39, which is almost, well, close. Just 3, 4, 5, 6, 7, like right about here. Okay, so here is the f of x. Okay, now let's graph the inverse. Well, our first point that we have here is at x is 0.14, y is a -2. So y is -2, x is 0.14, so it's like right here. X is 0.37, y is a -1. X is a +1, y is 0. We're at x is 2.27, y is 1, so maybe here-ish. And then x is at 7.39 and y is 2. So 1, 2, 3, 4, 5, 6, 7.39 and 2. So it looks a little bit like this. All right. So we solved for our points for our original f of x. The inverse is just them switched. Okay. Number 37. The parent function f of x equals log base 3 of x has been transformed by reflecting it over the x-axis, stretching it vertically by a factor of 2, and shifting it up 5 units. What is the equation of the new function? Okay, so we have to look at how these different parts play into what this function is going to look like. Well, looking at the first one, it says stretched vertically by a factor of 2. Remember that when our factor was on the inside, it compressed the graph. So for it to be stretched, then the constant needs to be on the outside. Okay, so stretched by a factor of 2. Reflected is what's giving us this negative number. And it's shifted up 5 units. Now remember, our ups and downs are positive or negative. Up is positive, down is negative. It's the inside one where it's going left and right that's opposite. So the answer is C, plus 5. Okay? All right, we're on to, go ahead and finish the rest of these problems on your own, and then we'll move on to the last part of this section. Page 90 starts us off with function combinations. All right, adding and subtracting functions is basically what this is about. Combining functions by adding or subtracting is very intuitive. If f of x and g of x are functions, then combining f plus g of x is the same as f of x plus g of x, and the same thing happens with subtraction. So let's take a look at what that means. Okay, example here on page 91. If f of x equals x and g of x equals 2 to the power of x, draw the graph of f plus g of x. Well, f plus g of x is x plus 2 to the x power. You're going to make your chart, plot your points, and figure out where they cross. Now, they just want you to graph the new one. They've graphed them all, right? Here's f of x, here's g of x, and then here is the f plus g of x, right? That's more than necessary. Finding the points for those parts are not necessary. All we are caring about are these points here. Don't do more work than you need to, okay? So you're going to set up your chart and figure out your points. For this example, we have f of x equals x squared and g of x equals the log base 2 of x. Draw the graph of f plus g of x. Well, f plus g of x is x squared plus the log base 2 of x. Again, they did the f of x and the g of x. Not necessary when they're only asking for the graph of the combination. Turning the page, I think they're just doing it so you can see the difference, right? Turn the page, and here we can see, because we've plotted our points, and these points are what matter, this is what the graph of the f plus g of x looks like, right? It swerves in kind of 2 different ways, all right? Plot your points, graph them. Multiplying, or not plot them, but calculate your points and then plot them. Multiplying and dividing functions, they can also be multiplied and divided, just as they can be added and subtracted. So this example down here, f of x equals 4x plus 1, and g of x is the step of x. Multiply them together, okay? Well, as you can see here, they're not going to multiply the step. They're not going to distribute that through. That's something that we need to figure out when we do our points, okay? And again, because it's a step, the points need to be like they are giving you the intervals, but you're not gonna know the intervals. You're gonna have to do the points like we did in the step. What is if x is -1, if x is negative 0.99, if x is negative, or not 0.99, but 0.9, if negative 0.8, you're going to have to figure out the steps, because look at this graph. That's crazy. You're not going to know these intervals just by looking at this, okay? You're not going to be able to find these intervals. There's no way for us to solve this to find these intervals, all right? So you're going to have to put it in point by point. It's nice that the book does it for you in their examples, but it doesn't help us when we're trying to do our work. We're going to have to put it in point by point. Okay? All right. let's do some of these problems together. Top of page 93, we have if f of x equals log base 4 of x plus 3, the quantity x plus 3, and g of x equals 4 plus x squared over x minus 9, what is the common domain of the two functions? Well, let's look at the domain of this first f of x, right? F of x is log base 4 of x plus 3. This has to be a 0 or more, right? So that means that the domain of this, of the f of x, is going to be -3 to infinity. All right, they use a comma. I'm just thinking out loud, right? -3 to infinity, because anything that keeps it positive, we will be able to figure out. For our g of x, okay, we have to figure out the points, right? X cannot equal 9. So for its domain, it's going to be from -infinity to 9. I'll write it the correct way, right? And then that's also union with 9 to infinity, right? It can't be 9, which is why we have the parentheses instead of brackets, because 9 would make it undefined, but it can be everything else but 9. So that's how we write that. So now the union, what is the common domain? So where these things intercept, right, or overlap each other. Even though this one goes to -infinity, for them to overlap, we have to stop at -3. So -3 to +9 and +9 to infinity would be their common domain. Okay, so that is part B. Looking at number 40, if f of x equals 2x and g of x equals x plus 1, choose the graph of the combination of f plus g of x. So f plus, f of x plus g of x, I don't like the way they write it the other way. That's crazy. Anyway, is going to be 2x plus x, so 3x plus 1. That is a line crossing at 1. So here we go. Okay. Now they want the inverse. Same two things. We're still adding them, but they want the inverse. So the inverse would be x equals 3y plus 1. So 3y would equal x minus 1. Y would equal 1/3 x minus 1/3. Okay, all we did was switch the x and y and then solve for y again. We're starting at -1/3, so not this one and not this one, and definitely not this one. It must be C. We go up 1/3. Okay. Okay. Do the rest of that. Let's turn the page though and look at one problem we can actually work together. All right, so we're going to look at together with problem 47, and it reads, if f of x equals log base 10 of x and g of x equals x, draw the graph of the combination f times g of x. Okay, so we're multiplying these together. That is somewhat easier said than done, right? So we have, for the f times g of x, it's going to be x times the log base 10 of x, right? Just like before, we need to make our values. And f times g of x, right? I guess that's probably better. What we need to remember though is my x can't be negative. It won't work with this graph, right? We can't have a negative value in here. So let's start at 0 and work our way out, right? If x is 0, then what is the value here? Well, the value is going to be 0 because 0 times anything is 0. So at least we're starting at the origin point, okay? Let me get my calculator reared up here. Ready to go. Find a spot, it will work. Okay, now let's try 1, okay? So the log of 1 is 0 times 1 is 0, right? So even at 1, 1, we're at 0 again. Now, if we do the log of 0.5, because these two numbers are the same, I'm just wondering what falls in between there. So let's do the log of 0.5, and that equals a negative number times 0.5, because remember, we've got the x out front as well. So it's the log of 0.5, or sorry, when we choose x as 0.5, we get a negative 0.15. All right, let's do a couple more points. Let's do 2 and 5, just to get us down the graph a little bit. All right, so if we take log of 2, because remember, it's base 10, so we can just use the regular log button. That's that, times 2. So it is 0.602, so I'm just going to put 0.60. And then let's do log of 5 times 5. 3.49. All right, that's enough for me for now. Let's go ahead and graph these points. Let me get my graph ready. Now, if we were graphing a bunch of points, we could have moved our origin over here because we know we're not going into either one of these regions. So we could have moved it over, but that's fine. We're only graphing a few points. So we're starting at 0, 0, and we know at 1, we're also at 0. But in between, we're actually at a negative 0.15, so it does dip down a little bit. Then we're at x equals 2, y equals 0.6. So that's like maybe right here. And then I chose 5 and 3.5, basically. So 1, 2, 3, 4, 5. 1, 2, 3 and a half. So it's going to look like this. It's going to dip down and then go on its merry way back up. Okay? So that's the multiplication of f times g of x for this problem, right? We're going to make our list of points. We're going to solve for those points. We're going to plot those points and be set. All right? Wow, section 5 was a chonker one, okay? We finished it. If you have any problems or questions, please don't hesitate to contact me. That is the end of this book. So next time we will be in Unit 3. So otherwise, if you have any questions, let me know. Otherwise, until next time.